In this example, we're going to talk about pumping liquid from containers and specifically determining how much work it takes to pump all or part of the liquid from a container. This is something that engineers often need to know the answer to so that they can design or choose specifically the right pump, or even to compute the cost to transport some water or other liquid from one place to another. In order to find out how much work is required to pump the liquid, we imagine lifting the liquid out in one thin horizontal slab at a time. And we're still going to apply the equation work equals force times distance to each slab. So then we take that and we apply the integral concept, which of course where those slabs become infinitely thin in size and we can add infinitely more of them, right? That whole idea when we thought about integration as being the sum of all those rectangles and the width becomes infinitely small. So the width of these slabs, and you'll see here there's a slab, we'll call that delta y. You know, that can become infinitely small, and the thinner the slab becomes, just the more rectangles we have. And that's kind of what integration is, adding up all of those different rectangles. Okay, so in this case, we have a rectangular tank shown here. The top of it is at ground level, so the rest of the tank is below ground, and it's used to catch runoff water. We assume that fresh water weighs 62.4 pounds per feet cubed. But, you know, when we talk about gasoline or mercury, gasoline weighs 42 pounds per feet cubed, where mercury weighs 849 pounds per feet cubed. So very different numbers depending on the liquid. So it's always important to know what the liquid is. If we talk about salt water as opposed to fresh water, slightly more dense, right? You float easier on salt water. The density of salt water is 64 pounds per feet cubed. So always take that into account. In this problem, we are going to figure out how much work it takes to empty the tank by pumping the water back to ground level. And we will assume we're dealing with a full tank. So once the tank's full, we empty it and let it catch more groundwater. If the water is pumped to ground level with a 511 horsepower motor, so that has a work output of 250 pounds-feet per second, how long will it take to empty the full tank? So we're going to round that to the nearest minute. And then the third part, we will show that the pump in part B will lower the water level 10 feet, which is halfway because you can see in the picture we are 20 feet below ground, in the first 25 minutes of pumping. And then we'll look at how the answers might be different if the water weighed less, if we were dealing with something that had a lower weight density. So let's approach each piece of this problem. First thing we're going to talk about is that slab, right? This rectangular prism slab that we have. So the slab between the planes at y, and then the distance y plus delta y, some change in y, has a volume. And it's a rectangular prism, so it's length times width times height. So delta V equals 10 times 12 times that vertical change, delta Y, or rather 120 delta Y. And the 10 and the 12 just came from the length and the width of the tank, and then that height is delta Y, the change in there. So what is the force, right? Let's look at that. We've got our force required to lift the slab. And what we're going to know is that is equal to the weight times the volume. So force, my weight density, 62.4, times delta V, that is 62.4 times 120 delta V pounds. And we have a third part that we need to consider here, and that's going to be the distance through which the force must act. So the distance through which the force must act is about y feet. It's variable, we don't know. All right, so what we can then say is the work done to lift that slab of water, the work done to lift the slab, delta W, is going to be the force times the distance. So the force is, we just found that, 62.4 times 120 delta volume times that distance, which is y, and that is feet pounds. And just a note, I noticed while I was working on something up here, this delta V we said was 120 times delta y. I should have written a y right there. So we've got delta y pounds, and so when I was looking up at my work, this right here should also be delta y. All right, so this is telling us the work done to lift the slab, right? Just one slab of water, but we have tons of slabs of water, right? And as the delta y becomes smaller, the quantity of slabs becomes greater. So the next piece we would look at here would be the work that needs to be done to lift all of the slabs of water. So work is going to be approximately the sum from 0 to 20 of all my delta W's, which is the sum from 0 to 20 of 62.4 times 120 delta y times y feet pounds. And this is just the Riemann sum over the interval from 0 to 20. So essentially all this is we're doing the integral of this, right? And delta y, that just is the part, the integration with respect to y, when we think back about our Riemann sum definitions. So finishing up part A, the work that is required to pump the tank empty is the limit of these sums that were on the last page. So the work is the integral from 0 to 20 of 62.4y times 120, and the delta y turns into my dy. So I've got some constants, 62.4 times 120, they'll come in front, and we have the integral from 0 to 20 of y dy. Might help you to see that if we had those brackets there, which that product in the front, 62.4 times 120, integrating this is y squared over 2. And we would evaluate that integral from 20 to 0. Plugging in 0 is going to give me 0. So my solution here is 62.4 times 120 times 20 squared over 2. And we get 1,497,600 foot-pounds. That is the work required to empty the tank. So on the next slide, we'll do parts B, C, and D. So for part B, if the water is pumped to ground level with a 5/11 horsepower motor and has work output of 250 feet-pound per second, how long will it take to empty the tank? So in this situation, what we know is that time is equal to work divided by the work output. So that is foot-pounds divided by foot-pounds per second. And that's going to give me the time in seconds. We want to answer, you notice here, to the nearest minute. So we have our work. We found that in the last part of the problem, 1,497,600 divided by the work output of 250. This gives me 5,990.4 seconds. And if I want to convert that to hours, I divide by 60 into minutes, divide by 60 once again, and that will give me 1.664 hours, or that the time is approximately 1 hour and 2/3 of an hour is 40 minutes. So it takes approximately 1 hour and 40 minutes to do this quantity of work. All right, let's move on to part C. We want to show that the pump will actually lower the water level halfway during the first 25 minutes of pumping. All right, so in order for us to do this, we need to know the work required to empty the tank halfway. And that's going to be the same integral that we just used, but instead of 0 to 20, that entire distance, we're going to say 0 to 10, about halfway. Okay, so we've got 0 to 10, and the way I had my integral set up was 62.4 times 120y dy. And this, of course, is 62.4 times 120 over 2 y squared evaluated between 10 and 0. The 0 is going to go away, so we only need to plug in the 10. 62.4 times 120 y squared gives me 100, all divided by 2. And we end up with 374,400 foot-pounds of work. So the time in that situation, the time would be the actual work, the 374,400, over the work output, which was the 250 associated with the pump motor. And that gives us 1,497.6 seconds when we divide it. Converting that into hours would be dividing by 60 twice, and that gives us 0.416 hours, which is approximately 25 minutes. If I take that and multiply that by 60, I get 24.96, right? So we can empty half the tank in 25 minutes. And then part D of our problem, simply asks us, how would the answer in A and B be different if the water weighed less? Well, if the water weighed less, it would take less work. It wouldn't be as hard to lift the water out of the tank. And subsequently, less work would require less time. So I hope that helps you with some of the pumping liquid problems you're going to see in your homework.